So we've just been talking about functions and what it means for a relation to be a function. Now, and we looked at function notation last class period. Now we're going to look at what is called the difference quotient. So the difference quotient, if you have some function f of x, it's given by the following. You're looking at f, parentheses, you have this argument x plus h that you're plugging in wherever you see an x and f of x. And then you're subtracting off minus the equation of f of x. And you're putting this all over h. So this is our difference quotient. It actually ends up being that it's the average rate of change between 2 points, x and f of x plus h, on some function f of x. But don't worry if you don't understand that. Hopefully in the future you will. So again, this is something that you'll be seeing over and over again when you start calculus. And so it's good that you get this down. The problem that most students have is this first piece of this difference quotient, which is this f of x plus h. In the beginning, when you're doing this difference quotient, sometimes breaking it down into pieces is helpful and then putting it all together. So let's look at the example below. And it says, find the difference quotient of f for each function and be sure to simplify. So the first f of x that we're given is x squared minus x plus 4. So if I was looking at f of x plus h, okay, so I'm going to share what one of my students who is a tutor for us taught, and I heard her teaching my other students this last semester. And I thought that this was really kind of cute and maybe a way to help you remember what you're doing. Think of f, that function, is our pirate. This equation right here, it's the map where the pirate is going to bury his treasure. And x marks the spot where he wants to bury the treasure. So we're going to go in here, and wherever we see an x, we're going to dig a hole. And that hole is going to look like a parentheses. So I see an x here, it's squared. So I'm going to have a parentheses squared minus, I see another x here. So think of it as the pirate's digging a hole to bury his treasure, plus 4. Well, this treasure that this pirate wants to bury is this piece in here, f of whatever we're taking, in this case, x plus h. So the pirate's treasure is x plus h. He's going to drop it inside the hole. And so that's a little trick. Maybe that little story will help you when you're doing these and evaluating functions at particular numbers or expressions. Okay, so I don't know who actually came up with that or how she learned that, but I thought that that was a cute little story and maybe a way to help you remember what you're doing here. Common error is that students want to distribute that f of x or that f into the parentheses x plus h, but that is totally wrong. Okay, the other thing that you want to make sure that you're not doing is that x plus h quantity squared. We can't just square each piece because of that plus in between. We have more than one term. So we have to write this out. That square is saying when I'm taking what's inside the parentheses and multiplying it by itself. In this case, twice. The other thing is you need to make sure that you're distributing your negative if you have one. And so this would give us negative x minus h, bringing down the plus 4, is equal to, and so let's go through and distribute and combine like terms for this piece. So we have x times x times h. So that's going to give me x times x is x squared, plus x times h is xh. Now distributing the h to each term, So I have h times x is hx, but I'm going to write it as xh, same thing, plus h times h is h squared. And then let's bring down the rest. So negative x minus h plus 4. So going in here, we're just going to combine like terms. There's only two like terms that we have, which is the xh plus xh. So let's bring everything down. X squared plus combining xh plus xh. Well, 1 plus 1 is 2. Carry down what they share in common, like term xh, plus h squared minus x minus h plus 4. So this is our f of x plus h. So this is just this piece up in here. So let's start putting it together. So this f of x plus h is what we just had. This x squared plus 2xh plus h squared minus x minus h plus 4. Then it's telling me that I need to subtract off my f of x function. So I'm going to subtract off minus this whole function f of x. So I need to put parentheses because there's more than one term in that function around my equation. So x squared minus x plus 4. And then it tells us we're taking that whole thing and we're putting it over the variable h. So it looks really nasty. But once we go through here, things are going to start simplifying out really nicely. So I technically don't need those first brackets in the numerator, but those second brackets, I need to distribute that -1 to each term. And so this is another place where students tend to make an error by forgetting to distribute that negative sign. So we get, sorry, my pen for some reason is not working. So let's bring down the first piece. We don't need those brackets. We have x squared plus 2xh plus h squared minus x minus h plus 4. Distributing this negative, I get minus x squared plus x minus 4 all over h. So looking at this, we have multiple like terms. We have a x squared minus an x squared. So those end up canceling each other out. We have here a negative x plus a x. So those cancel each other out. We have a negative h. Oops, that's not what I wanted. We have a negative 4 at the end. And we have a positive 4 here. And those cancel out. So left in our numerator, we have 2xh plus h squared minus h all over h. So we're almost done. If you did everything correctly, you should have a factor of h on top that you can pull out and simplify with the 1 on the bottom. So notice that each term in the numerator has at least one h. So we can pull the h out of the numerator, terms in the numerator. So if I take an h out of 2xh, I'm left with just a 2x. Plus, if I factor in h out of h squared, I'd be left with 1h. Minus, if I take an h out of negative h, I'm left with minus 1. All over h. So now we have a common factor in the numerator, which is h, and the denominator, which is h. And so this reduces down to 2x plus h minus 1. Okay, so we found the difference quotient of that function f of x. Okay, so let's look at a couple more examples of finding the difference quotient. In these next examples, we're going to have to use some tricks to help us simplify, tricks of algebra. And so our first example, we have 1 over x plus 3. Again, we want to find the difference quotient. So again, the difference quotient is f of, we're going to plug in x plus h wherever we see an x, and f of x, minus, we're going to subtract off our function f of x, and we're going to put this all over h. Okay, so for this first piece, f of x plus h. So we're going inside our function, and wherever we see an x, we're dropping in x plus h. Okay, so this is, again, let's just follow along with our story. So this pirate, his map to bury the treasure is 1 over x plus 3. And so we have 1 all over. We see x here, so the pirate's gonna dig his hole. X marks the spot, plus 3. And now he's burying his treasure of this x plus h inside of the hole. So that's just the first piece of the difference quotient, f of x plus h. Then we're going to have minus our function f of x. Well, the equation there is 1 over x plus 3. And then we have this whole thing over our h value. So we want to clean this up and simplify. So we have a fraction, or fractions in this case, within a fraction. And so we don't want like fractions within a fraction. So we want to rewrite this as a single fraction. There's multiple ways that you can do this, but the way that I'm going to be doing it in this class is multiplying by our fancy 1. So what you want to do is you want to figure out what is the least common denominator, or what is a common denominator. It doesn't have to be least, but least is the easiest, of the fractions within the fraction. So I have 2 fractions within this main fraction. And so if I'm finding the LCD of these 2 fractions, this would be this x plus h plus 3 all times this denominator here, x plus h. So we're going to multiply this by a fancy 1, and that fancy 1 is the least common denominator divided by the least common denominator. So the whole reason that we're doing this is that when we go and distribute this to the numerator, our fractions are going to simplify by canceling out like factors and get rid of our denominator. So we want to distribute this piece, the least common denominator, to each term in the numerator. So if we did that, we would have 1 all over x plus h plus 3. This would be times our LCD, which was the x plus h plus 3, that quantity times x plus h. Then we have this minus. We have our next term, which was 1 over x plus 3. We're distributing the LCD to this term too. And so we have x plus h plus 3 all times x plus h. All over, and now we're doing this to our denominator. So our denominator here, we have our h times our least common denominator, which again was x plus h plus 3, that quantity times x plus h. So notice the denominator in our first term cancels in the numerator with this x plus h plus 3. So we're technically left with this 1 here times this x plus h. So that 1 times the x plus h, so I have some room, is just x plus h. And then, excuse me, in the second term, this, when we distributed, we have 1 over x plus 3. Oops. That should have been right here, my LCD. This should have been x plus 3. X plus 3. X plus 3. Okay, that is the common denominator. So what we're left with here then is x plus h canceled. We're left with x plus 3. Then we have this minus. So x plus 3's cancel. And so we have this bracket around x plus 3. Actually, x plus h. Then plus 3. All over. Let's just keep our denominator. Let's not distribute out. So all over x plus h plus 3 times x plus 3. Because of this minus in here, we can't simplify, and the plus either. We can't simplify. These are not like terms in the numerator with the denominator. We need to distribute our -1. So let's bring down our x plus 3. Distributing -1, we get negative x minus h minus 3 all over h times x plus h plus 3 all over, or times x plus 3. So combining like terms in our numerator, notice we have an x minus an x, those cancel. We have a 3 minus a 3, those cancel. And so we're left within the numerator a negative h all over h times the quantity x plus h plus 3 times the quantity x plus 3. We're almost there. Now we have a like factor of h in the numerator and the denominator. And so we can cancel out our h. We're left in the numerator with a -1 all over the quantity x plus h plus 3 all times x plus 3. So this is our difference quotient of our function f of x is equal to 1 over x plus 3. Okay, so let's look at another example. This time we have f of x is equal to the square root of x plus 1. So again, we want to find the difference quotient. So we want to find what is f of x plus h minus f of x all over h. So our new map for this pirate is the square root of x plus 1. We're going to go in wherever we see an x for the first piece. We're going to dig a hole. So we have the square root. We see an x here, dig our hole. Plus 1. We're going to bury the treasure of x plus h. Minus f of x. Well, f of x, my equation is the square root of x plus 1. And we're putting this all over h. So looking at what we have, we can no longer, or we can't simplify. But a trick in this case is to get rid of the radicals. And to get rid of the radicals, we're going to want to multiply by the least common denominator. No, ignore what I just said. Sometimes I'm doing too many things at once. Just stop and just talk. We're not multiplying by the common denominator. We're multiplying by the conjugate. So we want to use the fact that if we have multiplied a minus b times a plus b, and we distribute that out, this gives us back the form a squared minus b squared. So if we multiply by the conjugate of these radicals, so we change the sign that's in between. This was a minus, so if I change the sign in between my two radicals to be a plus, we'd have the square root of x plus h plus 1 minus that conjugate, so it's going to be plus the square root of x plus 1. But I don't want to change my expression, and so I can make an equivalent expression by multiplying this fraction by a fancy one, which is just happens to be the conjugate of the numerator. So I could go here and I could distribute out and combine like terms, or even easier yet, we can use this rule. We're multiplying by the conjugate. The first term and the last term are the same in each of those binomials. So I can take this x plus h plus 1, and I can square it. Minus, I can take the second term, which is the square root of x plus 1. I can square it all over h times the square root of x plus h plus 1 plus the square root of x plus 1. So if I square a square root, remember we're just left with what's underneath the radical, which is called the radicand. So we're left with x plus h plus 1 minus, make sure you put parentheses here, squaring that square root, we're left with what's underneath the radical, which is x plus 1. We need parentheses so that negative is distributed all over h times the quantity x plus h plus 1 plus the square root of x plus 1. Do not distribute that piece in the denominator. That's just going to make more work in the end where you're going to have to go back and change it. But we do want to distribute our negative inside the parentheses here. So multiplying everything through by -1 in that piece. So let's first bring down the other pieces of the numerator, x plus h plus 1. Distributing a -1, we get negative x minus 1 all over h times the quantity square root of x plus h plus 1 plus the square root of x plus 1. So like before, things in our numerator are going to start canceling out. Notice we have an x minus an x, cancels. We have a 1 minus a 1, cancels. So all we're left with in our numerator is this h. We have a common factor in our denominator of just our h. So we're going to be able to simplify by canceling out the h, because that's all we're left with in the numerator, h all over h times the square root of x plus h plus 1 plus the square root of x plus 1. Our h's cancel. Technically, there's that 1 out here that we don't have written. So when we cancel out the h in the denominator and the numerator, we're left with 1 all over the square root of x plus h plus 1 plus the square root of x plus 1. So this would be the difference quotient of f of x equals the square root of x plus 1. So now we're going to look at some notation with functions and properties of adding functions together, subtracting functions together, multiplying and dividing functions together. So given functions f and g, the sum of the function is defined by, so notation-wise, when you're adding your function f plus g, you might see it written as f plus g of x. This is saying that all we're doing is we're taking the equation f of x and we're summing it to the equation of g of x. It is wrong to think of this as I'm distributing my x inside the parentheses of f plus g. This is just notation of I have some equation or some function f of x and I'm summing it to some equation g of x. So if I'm looking at the domain of summing f of x plus g of x, the domain consists of all real numbers x that are in the domain of both f and g. So that is, we're going to look at the domain of f of x. Intersection the domain of g of x. So this again is what they have in common. So remember the symbol, this upside down kind of U shape, stands for the intersection. The intersection means that the set of the elements, we're taking the set of the elements that they have in common for both of them. So look at the domain of f of x, look at the domain of g of x, and take what they both share in common to be the domain of f of x plus g of x. So for the definition of the difference of two equations, if we're given f and g, the difference of the function, we could write it as f minus g of x. And this is the same thing as thinking of taking f of x minus the whole equation g of x. Same thing as before. The domain is going to consist of all real numbers x that are in common with both f and g. That is the domain of both of those. So for the product f and g of two functions, we would define that as parentheses fg. You could put a dot there if you want to in between of x. This is just saying I'm taking my equation f of x and multiplying it to my equation g of x. So the domain of f times g of x is just like the ones above. You're going to look at the domain of f, the domain of g, and take what they both sets share in common for the domain. And the last case scenario is the quotient, taking the quotient of two functions. So given a function f and g, the quotient of a function is defined by, so we can write it as f divided by g of x, which means I'm just looking at my equation f of x divided by my equation g of x. So this is the one that we actually have to be careful. There's a little more stipulation than the domain of the ones above. In this case, g of x cannot equal 0. We can't divide by 0. So when we're looking at the domain, so the domain consists of all real numbers x for which that are also in the domain of f and g, that is. Okay, so the copying and pasting didn't go great in here. Looks like it left some stuff out. So the domain, we're going to look at the domain of f and domain of g, but also exclude from the domain values of x, which make g of x equals 0. So you're looking at the intersection of the two sets of the domain of f and g, what they share in common. And if needed, we're going to exclude the value which sets our denominator equal to 0. So let's look at a couple of examples. So let's look at some examples where we're looking at finding the operations, adding, subtracting, multiplying, dividing two functions, and then finding the domain. Well, let's first look at, because for this whole thing, we're going to need to determine the domain of both our functions. So let's first look at the domain of f of x. So recall, when we're given an equation and we're trying to find the domain, we first see, does that equation have any trouble spots? Are there any variables in our denominator? And in this case, yes, there is. So we need to see, is there anything in here that we could plug in for x, which would set that denominator equal to 0? Yeah, x plus 2 is 0 and x equals -2. So for the domain of f of x, it's going to be all real numbers x, such that x does not equal -2. So now let's look at the domain of our g of x. So g of x also has a trouble spot. It has a variable in the denominator. So we need to exclude the value which sets that denominator equal to 0. And that would be when x is equal to 1. So our domain is going to be all values of x such that x does not equal -1. So I'm looking at what they all share in common. Well, we share everything in common, the whole number system, except for -2 and -1. So the domain of these operations at least the f plus g, f minus g, and f times g. We can put that x at the end if we wanted, but this means the same thing. The domain of all three of these, this is going to be all real numbers x, such that x can't be -2 or -1. Okay, so let's look at part A where we're summing f plus g of x. And so this is just saying I'm looking at my function f of x plus my function g of x. So looking at my function f of x, I have this is 1 over x plus 2 plus my function g of x, which is x all over x minus 1. Okay, so we want to combine this and simplify. In order to combine fractions, you need a least common denominator. Well, x plus 2 and x minus 1, those don't have anything in common. Like factors. So our LCD is going to be x plus 1, x minus 1. So I need a common denominator in each case. And so 1 over x plus 2, and this is missing x minus 1 in the denominator. So I'm going to multiply this fraction by a fancy 1 of x minus 1 over x minus 1 to get the LCD. Plus, I have the x over x minus 1. But for this denominator, I'm missing x plus 2. And so I need x plus 2 down in the denominator. So I'm going to multiply this fraction by a fancy 1 of x plus 2 over x plus 2. So let's distribute in our numerator 1 times x minus 1. Well, that's just x minus 1. Plus, let's distribute in our second numerator. So distributing my x to the x plus 2, I would get x times x is x squared plus 2 times x is 2x. All over our least common denominator. Don't distribute the denominator. Leave it as x plus 2 times x minus 1. Or x minus 1 times x plus 2 also works. Let's combine like terms in our numerator. So there's no other term like x squared, so bringing it down. I do have, though, an x plus a 2x, so that gives us plus a 3x minus 1 all over x plus 2, x minus 1. So we just found what f plus g of x was equal to. If that numerator would have factored, or at least factored, and had the same, a common factor as the denominator, I would have done that and I would have simplified there. But x squared plus 3x minus 1 does not factor. So now looking at f minus g of x, doing the exact same thing, but now instead of adding the two fractions, we're looking at f of x minus g of x. So our f of x function, this was the 1 over x plus 2. I'm going to leave some room here because I know I need a least common denominator, minus g of x, which is x all over x minus 1. In order to add or subtract fractions, we need our LCD. We found what the least common denominator was before, which was x plus 2 times x minus 1. So for the first fraction, to get my LCD, I need to multiply both the numerator and denominator by x minus 1. For the second fraction, to get the least common denominator, I would need to multiply by a fancy one of x plus 2 all over x plus 2. So multiplying the numerator in the first fraction, I'm left with 1 times x minus 1, which is x minus 1. For the second fraction, carry the negative, the sign outside. So let's carry the negative and distribute negative x to x plus 2. So negative x times x gives us the negative x squared, and negative x times 2 gives us minus 2x. All over our LCD of x plus 2, x minus 1. We're almost done. Just combine like terms in our numerator. There's no other term like negative x squared, so I'm bringing that down. I see I have an x minus a 2x, which are like terms. So negative 2x plus 1 is negative x minus 1 all over x plus 2, x minus 1. So the next piece wanted us to multiply our two functions. So actually that's easier than what we've been just doing. So if I want to look at f times g of x, I'm just looking at my f of x function, which is 1 over x plus 2, times my g of x function, which is x all over x minus 1. We do not need a common denominator when we're multiplying fractions. All we're doing is we're multiplying across in our numerator and multiplying across in our denominator. And so over here, we get 1 times x, which is x, all over x plus 2, that quantity times the quantity x minus 1. And we're done. So the domain of all of those functions, f plus g of x, f minus g of x, and f times g of x, we had found above was the set of all real numbers except x was not negative 2 or negative 1. F divided by g of x. The domain is going to be a little bit different, but let's first write this out. Again, same functions. Let me just copy and paste. Now we're looking at f divided by g of x. So if I look at f divided by g of x. So looking at my equation f of x divided by my equation of g of x. My equation f of x is 1 over x plus 2. My equation of g of x is x all over x minus 1. Since this is a single fraction divided by a single fraction, we can just rewrite this a little differently. This is the same thing as 1 over x plus 2 divided by the fraction in the denominator, x over x minus 1. recall there's some rules of division when you're dividing two fractions. If you had something in the form of a over b divided by c over d, we rewrite division of fractions as copy down the first fraction times the reciprocal of the second fraction, flipping the second fraction, d over c. So using this rule, we would copy down our first fraction, 1 over x plus 2, times the reciprocal of the second fraction, which is x minus 1 is now in our numerator, all over x. So let's simplify. Let's just multiply straight across. This 1 times x minus 1 is x minus 1, all over the quantity x plus 2 times x. So for the domain, we need to be careful because there was one extra stipulation. G of x cannot equal 0. So we can't have our denominator equal to 0. And so we can't have x divided by x minus 1. Let's find out when this is equal to 0. And once we find out when that's equal to 0, we want to exclude it from the domain along with the 1 and -2. Okay, so we've dealt with solving rational functions earlier in the semester. And so we can solve an equation that has a fraction by clearing the fraction and multiplying through by our common denominator of all the fractions, which is just x minus 1. X minus 1s are going to cancel. We're left with x equals 0 times x minus 1 is 0. So g of x is equal to 0 when x is 0. So we also have to exclude x equals 0 from the domain. So our domain of f of x divided by g of x is equal to the set of all real numbers x, such that x does not equal -2, 1, and 0.